Hello, everyone, and welcome to Astronomy at the Beach 2020. My name is Liam Finn. I'm from the Ford Amateur Astronomy Club, and I'm actually going to be your host today, and I will field any questions that you have that you post during chat. Please, throughout the whole session for the next hour, if you have any questions, please feel free to put your name into the chat. Also, it helps us to, if you click on the like the thumbs up, and the subscribe button that you have there in the YouTube screen, because it helps us promote us on YouTube, which we always appreciate. So in this event, we're actually going to have Timothy Campbell, who is a member of our astronomy club, and he's actually going to give us a tour of the night sky, talk about planets and so on in our solar system. So at that point, I'm going to hand it over to Tim. Tim, take it away.
All right, thank you, Liam. So I'm Tim. I'm a member of the Ford Astronomy Club, as Liam mentioned. I'm also a NASA Solar System Ambassador, as is Liam. That means we don't get a paycheck. We volunteer to do this kind of thing. We'll try and make this an interactive presentation. So this will be probably a little different than some of the other planetarium shows you may have seen. Both Liam and I are actually planetarium operators in real life. We volunteer at Henry Ford College, and we do planetarium shows there, but with the global pandemic, we can't do those. However, I have connections to a company called Simulation Curriculum, and they make simulation software that's pretty good. And if you've ever been to a planetarium that uses the Spitz Dome system, this is actually the very software that they use. So this is actually real planetarium software that I'm using to demonstrate this. Tonight we're going to take a look at mostly the stars of fall, and I'll get into that in just a moment. We'll also explore quite a few planets, and as you ask questions, and I encourage you to ask questions, I like this to be as interactive as possible. We'll be able to just dynamically answer those questions and even show you objects of interest in the universe that you might be curious in seeing. So with that, let's go ahead and get started. I am going to share my screen, and there we go, and there we go. So you should now see pretty much a screen that looks like we're just about to have sunset. This actually, by the way, is a simulation of exactly what the sky would look like from Detroit. It's not a very accurate simulation, though, because in this simulation, you don't see any clouds. And if you peek outside the window, there's probably a lot of clouds. So we don't have to worry about the clouds, though, because we have our software. So with that, let's get started. One of the things I want to kind of show off here right away, if you look at this image, you can see, and this is obviously sped up. So in my simulation, 5 minutes is equal to 1 second in real time. So we're making the moon go across the sky very quickly. And this effect, if you watch the stars moving by, is called diurnal motion. That's the sophisticated word for the stars going by. And to us, it looks like we're standing on the ground and the sky is just moving right on by us. But that's not really what's happening at all. If I go into this simulation, you can see the same universe and the same Earth, but this time we're hovering in an imaginary position, floating above the Earth's North Pole. And you can see the globe of the Earth below us, and it is spinning from west to east. And the universe itself beyond is not actually moving. Those stars are remaining still. This gives us the illusion that we're standing still and the sky, the heavens are moving from east to west, when in fact it's the opposite. The heavens are standing still. Do the heavens really stand still? Not really. They actually do move, but even the closest stars, other than our sun, are crazy far away, and the distances are so huge that we don't notice their movements, not on the time span of a single human lifetime. There are only a few stars that move fast enough relative to our solar system that we pick up on it. Now, it can be measured with very, very precise scientific instruments, but it's not noticed by humans. I once had somebody that asked me, there is a star cluster called the Pleiades star cluster, and they thought that they had read someplace that the Pleiades used to be located somewhere south of Orion's belt. And so I used my software and did a little bit of math and worked up something called the proper motion of the stars. Proper motion is the direction and velocity that the stars are actually moving. And what I worked out was that in order for the Pleiades to appear to move just 1 degree across the sky relative to the other stars would require 80,000 years. And so you can see that the stars do move, but not very fast. So the next simulation I'd like to show you is just a view of the inner solar system, and a couple of things that I want to point out here. So first of all, I want you to notice that the orbit of Mars here, the outermost ring, if I move this up a little bit, is it's pretty elliptical. So these orbits are not particularly round. In fact, all orbits are elliptical if I move it around. Also, you can see that Mercury, the sun is not really in the center of Mercury's orbit. Mercury is very elliptical. It turns out the planet with the most circular orbit in the solar system is Venus. Second closest is Earth, but neither one of us have perfectly circular orbits. The other thing I kind of want to point out and call attention to is, if I flip it around here, you can imagine that if you were standing on the Earth, that if you're on the side of the planet that's facing the sun, you're in daytime. And if you're standing on the side that's facing away from the sun, you're in nighttime. But think about what this means when you look out at the stars each night. So when the Earth is here in the solar system, and I'm just going to go ahead and put this simulation into motion, and I'm going to speed it up. Okay, so now I've got the planets now moving around the sun. That if you attempt to look in the direction facing the sun, what you're going to see is the glare of the sun, and you're going to see a lot of blue sky. There are clouds, or I'm sorry, there are clouds. There are clouds. There are stars on the other side of the solar system beyond the sun, but we can't see them because the sun is in the way. But if we look in the direction facing away from the sun, we do see the stars. And there are 360 degrees in a circle. There are 365 days in a year, 365 and a quarter, actually, just about. And that means that each one day, the Earth moves about 1 degree in its path going around the sun. And so after a season, 91 days, we would have gone from seeing the stars that were to the right of the screen to the stars that are towards the top of the screen. And in another 91 days, we'll be looking at the stars that are in the west of the screen. And for that reason, the stars that you see each season appear to change almost completely from season to season. There's one exception, which is stars that are above Earth's North Pole or South Pole. Stars in that direction, as long as it's dark outside, you can see those same stars every year. And I'll get to that in just a little bit. So this next simulation that I'd like to show you, oh wait, before we move on, there's one last thing I wanted to show you, is that if I tilt this all the way on edge, there's another thing that you don't quite get out of textbooks, but I do want to show it to you. By the way, this software is actually very accurate, right? So do you notice that the rings going around, they're not actually all in the same plane? So you can see that the orbit of Mercury is fairly tilted, and the orbit of Mars is tilted relative to the orbit of the Earth, and so is Venus. They're nearly in the same plane, but not quite perfectly in the same plane. And that's an important point that you're gonna recognize why that is a little bit later. So here's another simulation that says, why do we have seasons? So I've really sped up the Earth. I've also super enlarged it. So I've exaggerated the size of the Earth, and I've got the Earth moving around the sun in fast motion. But what I want you to notice as we're going around the sun is that the Earth is not straight up and down. It is tilted on an axis, and the angle of that tilt is about 23.5 degrees. But the other thing I want you to notice is that that tilt doesn't really change. You'll notice that it's kind of tilted toward the left on the North Pole and toward the right on the South Pole. And as it goes around the sun over and over and over, the tilt stays the same all year long. And that is, in fact, what the Earth really does. Now I'm going to stop this for a minute, and I'm going to manually set the date to June the 21st. That's close enough. That is approximately the date of the summer solstice. That is, if you live in the northern hemisphere, it's the longest day of the year. Now the day varies just a tiny bit depending on whether it's leap year or whether it's about to be leap year or just was leap year. But what I want to point out to you is that on the north side of the Earth, the northern pole is tilted toward the sun. And we live roughly 42.5 degrees north of the equator, not quite halfway between the equator and the North Pole. So we're just right about here where I'm wiggling my pointer, if you can see that. And that means that the sun, so this is the first day of summer, the sun will appear very high in the sky. And also, the daylight hours will be very long. We have a lot of daylight on this particular day. And this causes the sun to heat this part of the Earth even more. In fact, when the sun is coming from high above, it's heating the ground more efficiently. And that's why it's hot in the summer. So you may have heard that maybe the Earth is a little bit closer to the sun in the summer. In fact, the opposite is true. In northern hemisphere summer, we're actually a little bit farther away from the sun. But the difference is so small that it doesn't really change our temperature. What really changes our temperature is the fact that the northern pole is tilted toward the sun. Now, if you look at the opposite side of the Earth, down in the southern hemisphere, you can see that the southern pole is pointed away from the sun, and down there they don't get very many hours of daylight, and for them, the sun will appear very low in the sky. Now, I'm going to change the date. Let's move it to December the 21st. So this is roughly when the first day of winter would be. And now we have the opposite problem. In the northern hemisphere, our polar axis is pointed away from the sun, and us being 42.5 degrees north of the equator, we're way up here. We don't get a lot of hours of daylight up here. Also, the sun appears very low in the sky. So since we don't get very many hours of daylight and the sun appears low in the sky, the sun doesn't have a chance to heat this part of the planet as much, and that causes the weather here to be very cold. So fall, if we go back to fall happens halfway in between. So this is September the 21st. Again, give or take a day. This is when we refer to as the autumnal equinox. The autumnal equinox is the two poles are, neither pole is pointed more closer or farther from the sun than the other. And that means the entire Earth, doesn't matter where you are on the planet, you will get exactly 12 hours of daylight and exactly 12 hours of nighttime on that particular day. So the day and the night are the equal length. It's also the day when where the sun would appear directly overhead on the equinox will be a point that will be somewhere directly above Earth's equator. But as you go later into the fall, the sun will appear farther and farther south of the equator. And we can zip the sun around to the other side into the springtime, and the opposite happens there. Now the sun crosses into the northern part of the sky, and the northern hemisphere gets most of the benefit of the sunlight.
Tim?
Yeah.
Has Earth always been tilted in that way?
That's a great question. So on the scale of a single human lifetime, you could say the answer is yes. In your lifetime, it's always been tilted that way. But it turns out that's not actually precise. So with precision, there is a cycle that the Earth has where it wobbles around like a top. And this wobble is a cycle that we refer to as precession. It takes about 26,000 years to complete just one single wobble in the cycle of the sun. Or I'm sorry, in the precessional cycle of the Earth. So it does move just a very, very tiny fraction from year to year, but since it takes almost 26,000 years to complete the cycle, in the scale of just one human lifetime, you can, for all practical purposes, say that it doesn't move.
So, since that tilt is aiming towards the North Star, right? Yep. Will the North Star always be our North Star?
So it will always be the North Star again in your lifetime, but it won't always be the North Star for the history of the planet. So in fact, right now, the North Star isn't exactly above Earth's North Pole. It's about 2/3 of a degree away. And the precessional cycle of the Earth is actually causing our North Pole to point ever so slightly closer to that star. At the end of this century, roughly the year 2100, the North Star will actually only be 1/2 a degree away from the North Pole. That is the closest it will ever get. And then after that year, it will start to move away again. It'll get farther and farther. So over the thousands of years, over the millennia, the star closest to Earth's north celestial pole will change over time. But again, these are very slow processes that take hundreds of years to even notice a small amount of change.
And to anyone who's viewing right now, please feel free to type any questions in the chat, and we will address them just as Tim addressed the questions I asked just now. So please feel free to type in your questions, and we will address them.
So remember I said that the Earth is actually going around the sun, but I also mentioned that there was that illusion of the diurnal motion, that we're the ones standing still, everything else is doing the moving, when in fact we know that everything else is mostly standing still. We're the ones that are moving. And so we have this cycle where the sun appears to move across the sky, and you can see the names of these constellations are somewhat familiar. So there's Libra, Scorpius, and Sagittarius, and Capricornus, and Aquarius. And the sun is following that green line exactly. And if you look at it closely, you'll see dates are on there. So there's February, and then to the left you have that, you can see Mars, but you'll also see the names of planets sort of hovering close. There's Pluto and Saturn and Jupiter and Mercury and Neptune. But what I want you to notice about those other objects is they're all actually very close to that green line. The green line has a name. We call that name the ecliptic. It is the path that goes through the constellations of the zodiac. There are actually 13, not 12, 13 constellations of the zodiac. And the word zodiac for the zoo, the zoo of animals or zoo of creatures that the sun will visit in a year. And so in June, so for example, it just went through June. In June, that's where the sun will be. It will be somewhere in that part of the sky. And we won't be able to see those stars behind the sun. What we'd actually see is a blue sky and the glare of the sun. We can only see the stars in the opposite direction, the nighttime direction. And so this is the concept of the ecliptic. And again, the planets are not exactly on that ecliptic plane for the same reason that when I showed that earlier simulation, the orbits of the planets do not actually orbit in this flat disk like you may have seen in textbooks. They are very close to the same plane. They're just tilted by just a very tiny amount, but that tiny amount is enough to cause them to not appear directly on that line. They're just a little bit off. Okay. So now returning back to our simulation, this is tonight, this is now. The sun is now setting, and it's getting darker and darker. And as it does, we can see a couple of dots starting to appear on the screen. You can clearly see the moon over there, but I'm going to stop the simulation right about now. And I want to point out a few things. So there, of course, is the moon. So you're clicking in the wrong spot. So there, of course, is the moon. Over here, I have a couple of the brightest dots that I saw first. Those are not stars. This one is Jupiter, and this one is Saturn. But there were a few stars that we saw, and I'd like to point some of those out. So one of the first ones, and actually if I just back this up just a little bit to make most of the stars disappear. Okay, now I've got a lot of them to disappear, but you can see this one here. This is a star named Arcturus, and that is one of the brightest stars that we can see. Way up here toward the zenith right now is another star called Vega. So from the movie Contact, right, written by Carl Sagan with Jodie Foster. That was the star that she had pointed her radio telescope to when she heard the mysterious signal, right? So that's Vega up there, and down here we have Altair.
Just one thing: the term zenith means directly above you. Just so everyone knows, zenith means straight up above you.
Yes, thank you for that. Yep. And so it is in fact relative to where you stand. So there's no one spot that's, oh, that's the zenith in the sky. Well, that's the zenith in the sky because that's where you're standing on the Earth. If you were standing in a different spot, the zenith would be, relative to where that person is standing. And so I just wanted you to kind of see those very first stars. They're there all the time. Stars are always in the sky. We just can't see them because they're lost in the glare of the sun. And so now we have more and more and more of the nighttime stars starting to appear. And our ancestors looked at these stars, these familiar shapes. They used them to time things. They knew when it was time to plant the crops and when it was time to harvest the crops. They knew, when certain stars appear in certain positions in the sky, the weather is going to start getting cold. It's time to get the crops out of the field and get them safely stored. So it was one of the first things that we did to be able to keep track of time itself. Before we had clocks or calendars written down, we could at least use the stars as a familiar reminder with what the upcoming trend was going to be in terms of the temperature and when to do things. Now, it turns out we studied these stars so much that we started to notice familiar shapes in the sky, things that meant things to us. And different cultures have different ways of identifying these constellations, and we call them constellations. And so you can see I've got these little blue connecting lines that make these shapes, and then an artist has made illustrations behind these. And I'll move the sky around, and there are actually quite a lot of them. It seems so overwhelming to see them all. There are, in fact, 88 of them. And when I was younger, I thought, oh, it must be overwhelming to have to learn all of these things. It turns out, depending on how you attack the problem, it might be a little bit easier than you think. While there are 88 constellations, that's the same number of keys on a full-size piano keyboard, 88 constellations. Remember, a lot of those constellations are only visible in the southern hemisphere. You'll never see them unless you go on a trip. So you don't have to worry about memorizing the positions of those constellations just to find your way around in the northern hemisphere. The other thing is, remember, the constellations change each season of the year, except for the ones directly above the Earth's northern region or southern region of the sky. Those are the same all year long. And so it turns out, if you learn just a few of the constellations in what we're going to call the circumpolar section of the sky, and that's this section here, and I'll explain what this is in just a moment, as well as just a handful of other constellations, maybe just five per season, that after a year, you will find that you actually know how to find 20 or 30 constellations. And a lot of the constellations are minor. And so minor, they just sort of fill in the gaps between the other constellations. And so you'll quickly be able to determine what the major ones are. And now I find, Liam is the same, that when we go out in the night sky, after just a few stars appear, just enough to identify one or two constellations, it quickly in our brain fills in the rest of the sky, and we're able to locate all kinds of things. And you would think that we spent a lifetime doing this, but we didn't spend a lifetime doing this. This is something that I learned in, I would say I learned most of it in a year. And again, maybe just 5 or 6 in a season. That's not too bad. And after a year, I knew most of them. And then in the second year, it reinforced my memory of them. And I would say after 2 years, I knew it pretty well.
Yeah, and on top of that, like not only like when you do go out with astronomy clubs or whatever to do observing with them, not only do you remember the constellations, but you remember where in constellations certain objects are, like gas, like nebula, and all this kind of stuff. So it's kind of cool. You'd be amazed how fast you can really pick up on this. It sounds overwhelming, but it's not that hard.
So continuing on with this, this area that I've circled in red here is called the circumpolar region of the sky. And it's called that because inside this red line, these stars never actually set. They are visible all night and all day, every day of the year. Now, you don't notice them in the day because, again, the bright blue sky, but they are actually there. And the reason that it's drawn in this particular size is because where we are. So here in southern Michigan, we're roughly 42 degrees north latitude. And so this circle is drawn 42 degrees away from the celestial pole because the North Star, which is located right in the middle, and I'll show you how to find that in just a moment, so that even if you don't have a big circle in the sky, you'll still be able to find it. But that celestial pole there is about 42 degrees above the horizon because we are 42 degrees north latitude. And it just sits there and goes around. So I'll put it in motion for you, and you can kind of see it going around and around and around. And that star in the middle that we call Polaris doesn't really seem to move much. It does move a very tiny amount because it's not precisely above Earth's North Pole, but gosh, is it ever really close. So let's talk about how we actually find this. So in order to find this thing, one of the first things that we want to find is something that we call the Big Dipper. So the Big Dipper is now highlighted here on the screen for you. And you're thinking, oh, this is the first constellation. Sorry, wrong. This is not actually a constellation at all. This is something that astronomers refer to as an asterism. It's just a shape that's so familiar, so easy, that even though it's not a it's not an official constellation, we refer to it anyway. And so it gets the name asterism. It is actually part of a constellation. I'll get to that in a moment. But the Big Dipper has these 4 stars for a bowl and 3 stars for a handle. And little trivia point, if you look really closely at your screen here, this middle star in the handle is actually 2 stars. And back in ancient times, it was used as an eye test. So they would, when they're drafted into the Army, they're going to make you look at that spot in the sky, and they're going to say, hey, how many stars? And if you said 1, they handed you your spear and your shield. If you said 2, they'd say, oh, what do you mean there's 2? Well, there's a fainter star off to the side. Now, well, which direction is the fainter star? And if you knew that the fainter star was slightly above and to the left, they'd say, oh, he's got keen eyesight. And they would give you a bow and an arrow. Now, that was better than the spear and the shield, because with the spear and the shield, you were down on the front line. But if you got the bow and the arrow, you were way up on top on the castle ramparts, far away from the action. You had a much better life expectancy up there. And so I think that's probably when people started cheating on eye tests for the first time. In the meantime, if we use these 2 stars here, these N stars of the handle, and imagine, and this is a pretty easy to find constellation. It's pretty bright, actually. These stars are not very far away from us. And follow this up. It makes a point toward this star here. And this star in the middle is named Polaris. It is the North Star. But it is, not only is it the North Star, it is also the N star in another asterism called the Little Dipper. Now, the Little Dipper, again, 4 stars for a bowl and 3 stars for a handle, upside down of the Big Dipper. And let me see if I can just bring in both dippers. I'll light up the Big Dipper and the Little Dipper. It turns out the Little Dipper is also the constellation Ursa Minor. Ursa Minor means the little bear. The Big Dipper is actually part of the constellation Ursa Major. And Ursa Major just means the big bear, and I'll light that up. And you can see that there's the whole bear. He's got his front legs here, his back legs here. They're kind of going behind the hill because of the fall season here. His eyes and his nose here, the rest of his body, and he's got a really big tail, which is kind of strange because you don't normally see bears with really long tails. They're usually really stubby tails. There is some mythology behind why these bears have long tails. And the Little Dipper and the Big Dipper sort of chase each other around in the sky. Okay, so now that's our first 2 circumpolar objects. Again, you can see those all year, every year, but I promised you a show about the stars of fall. And the stars of fall are kind of special because the constellations of the fall sky, all the major ones, are all part of a great big story in Greek mythology. And so let's get on to our story. So the first constellation that is part of our story is Cepheus. And Cepheus is the king. And his constellation looks a little bit like an upside down house, though maybe not very well built. And with the rooftop sort of pointing in toward the northern part, kind of toward Polaris, not very precisely though. He is the king. And he is sitting on a throne, and this is meant to be the back of his chair, the back of his throne. His throne is facing you. And Cepheus is married to his queen, Cassiopeia, and Cassiopeia is also on her throne, but her throne is a chair sitting sideways, and she is facing her king. So there's Cepheus and Cassiopeia, and they are circumpolar. By the way, every astronomer who's an amateur astronomer knows how to find the Big Dipper, Polaris, and Cassiopeia. They're some of the easiest things to find in the sky because they're up every night of the year. So it turns out Cepheus and Cassiopeia rule this kingdom by the sea. And they have a daughter, and their daughter is very pretty. Her name is Andromeda. And Andromeda is so pretty, and her mother just can't get over how pretty she is, that her mother makes a boast one day and says, "My daughter is the most beautiful woman who ever lived. In fact, she is more beautiful even than the sea nymphs or the nereids." These sea nymphs, or sprites of the sea, are attendants to the god Poseidon. Neptune is his name in Roman mythology. So she, being a queen of this kingdom, just made a boast that her daughter is more beautiful than these little goddesses, these attendants to the god Neptune. And Neptune, you can imagine, is not very happy about this. So Neptune decides that these people need to be punished. And so his punishment, because he is a vengeful god, is he is going to flood the coastal lands and destroy Cepheus and Cassiopeia's kingdom, wiping out everybody. So Cepheus and Cassiopeia aren't too thrilled with the news, and so they decide to send someone to visit with the oracle. So the oracle are these priestesses actually, and they pray to the gods and they get messages from the gods. And so the oracle prays the gods, and the gods tell the oracle to tell Cepheus and Cassiopeia that they will be willing to spare the kingdom and not destroy everybody in it, but only on the condition that Cassiopeia and Cepheus sacrifice their daughter by chaining her to a rock next to the sea so that a sea monster named Cetus can come and devour her and kill her. So they must sacrifice the daughter. So they're not very happy with this either, but the alternative is everybody dies. So what to do? So it turns out, before we get too far in the story, let's figure out how to find the lovely Princess Andromeda. And so to do that, we're going to find another one of those things that we call asterisms. And this one is called the Great Square of Pegasus. And I'm just going to move a little bit to the east with our planetarium. And off to the east, you can see now the Great Square. Now, I realize that when you're looking at this, you're thinking, that doesn't look like such a square. Let me back out a little bit. It zoomed in a little bit more than I wanted it to. There we go. That's probably too much of a back out. There we go. Okay, you're probably thinking that doesn't look so much like a square, but what you have to remember is you are looking at a spherical sky mapped onto a flat computer screen. And so when you're actually outside in the night sky, it does in fact look just like a square. It doesn't look distorted like you see here on the computer monitor. In fact, if I kind of move it over, I can probably get it into a spot where it's maybe not so distorted and it looks a little more squarish. So that Great Square of Pegasus is part of a horse, and the horse is called the Pegasus. And I'll bring up the Pegasus itself. Okay, and there is the entire Pegasus. And this is the horse's head here. So this part here is the Pegasus's head. And these are his front legs. And what's missing from the Pegasus is his back legs. And so let me see if I can bring up the back legs of the Pegasus. And there they are there. But notice the label that shows up says Andromeda. And so this is actually the body of the maiden Andromeda. So we end the Pegasus here, and then the lovely maiden is here, and she is chained to a rock. In fact, if I can turn on some illustrations for you, let me see if I can do that quickly. Auto identify and show the illustration. There we go. So now I have the illustrations turned on for you so that you can see what they look like. So there is, oh, and I forgot to mention, the Pegasus is a winged horse. So he's a magical horse. More news on that in a moment. So now the Pegasus is chained to a rock, and there is a sea monster. I did promise you that there was one of those. And so the sea monster Cetus is down here, and he is on his way to devour the beautiful princess. But around the time that this happens, there is a hero in our story, and that hero is a guy named Perseus. Now, Perseus, over here, if I move this around, turns out to be the not so legitimate son of the god Zeus. Jupiter is his name in Roman mythology. It turns out Zeus had a bad reputation for cheating on his wife, so he wasn't a very faithful husband. And as it turns out, he had many other affairs. And it turns out that Perseus is his son through one of these little affairs that he had. So Perseus is the son of a human mother, but his father turns out to be a god, and not just any god. Zeus is the king of all the gods, and that turns out to work out in Perseus's favor, that your dad is the head god. And so what happens is Zeus wants Perseus, who plans to rescue Andromeda, to get a little bit of help. And so he cheats. So he starts giving Perseus some gifts. And so you can see Perseus has a shield. It turns out that shield has very special qualities. It is highly polished so that it works like a mirror. More on that in a moment. And he gives Perseus this horse that has wings and can fly. So Perseus has a winged horse and a very powerful shield that is so polished that it works like a mirror. And he is sent on a mission to go kill another Titan. By the way, the sea monster is in the family of what they call the Titans. And these are these monsters. And it turns out he has to slay this creature called the Medusa. The Medusa is also a Titan, but the Medusa is the body of a woman, except that she has hair, and with her hair is snakes for her hair. So serpents are coming out of her hair. And she has this gaze that if you look upon her, you will instantly be turned into stone and you will die. And so what Perseus does is he uses his shield as a mirror so that he can sneak up without looking at the Medusa and slay her. And so he slays her, chops off her head, and puts her head into a bag. Then he gets onto the Pegasus and he flies to the coast where Andromeda is chained to the rock. And when she's chained to the rock, he pulls the head out of the bag, shows it to Cetus, the sea monster, who is immediately turned into stone, and he sinks to the bottom of the ocean, never to be seen again. And so he has now rescued the beautiful Princess Andromeda. And in gratitude, the king and the queen offer Andromeda to be married to Perseus, and they, of course, live happily ever after. Isn't that a great story? All right, so, but we're not done yet. A little bit more to go.
Apparently, someone who was in our chat has always felt sorry for poor Medusa.
Poor Medusa. Yeah. So yeah, it is poor Medusa. All right, so one of the other things I wanted to point out about these constellations that are all over, and you can see there are lots and lots and lots of them. So again, these are the major, this is the major constellations of the fall. So if you can learn how to find the Great Square, the Cassiopeia, Cepheus, the Big Dipper, the Little Dipper, Perseus. We usually actually don't really point out Cetus in the planetarium because he's so low in the sky and hard to spot. You've pretty much learned all the constellations that you need to learn for the entire fall season. And then there's another set of characters that we do for the winter season and again for the spring and the summer. So moving on, one of the things I wanted to mention about these stars and these constellations that you see is, first of all, most of the stars that you see in the night sky, we live in a galaxy that is between 170 to maybe 200,000 light years across. And I remember when I was younger, we thought, 100 billion suns. Then they said, we're pretty sure it's more like 200 billion suns. And now, confidently, 300 billion suns. And the possibility that it might actually be 400 billion suns. That's a lot of suns in one galaxy that we live in. And it doesn't seem like it. Most of the stars that we see in the night sky are actually not that far away. If you live in a galaxy 200,000 light years across, you're seeing other stars that are a few light years to a few dozens of light years, maybe a few hundred light years. And just occasionally, some of them are a few thousand light years. So one of them that I'd like to point out now, if I can zoom into it, is this star here, which is, nope, that's not it. It might not even be labeled. I'm trying to find, maybe it's over here. There we go, Rho Cassiopeia, basically his elbow. If I can get this, why is this not? Do I need to zoom out a little bit? There we go. I've highlighted Rho Cassiopeia, and let me zoom out just a little bit so it's easier to find. There's a reason I wanted to point out this star. So there is the lazy W here. That is her sitting on her throne. And then right about where her elbow would be there, you see this very faint star. That star, Rho Cassiopeia, is, if you have exceptionally good human vision and an exceptionally dark sky, well away from city light pollution, very, very clear, dust-free, no smoke from forest fires, and nice and stable, then your excellent vision might be able to see that star without a telescope, without binoculars. That star, Rho Cassiopeia, is 8,100 light years away. It is the most distant star in the galaxy that you can see without using a telescope or binoculars. And the only reason that you can see a star that's 8,100 light years away is because that star is incredibly bright if you could be nearby. It is in a category of stars called yellow hypergiant. So you've heard of giant stars, supergiant stars. This is a hypergiant star. It's even bigger and brighter still, and it's a yellow hypergiant star. Only 7 are known to exist to astronomers, and that is one of them. So that is the most distant star that can be seen. The
Can
other
I
thing
add one thing?
Yeah.
The people often wonder, like, since the king and the queen defied the gods and Perseus helped them to defy the gods by not punishing their daughter and destroying the sea creature, Cetus, why they're still in the sky. Do you want to explain that part of the story?
Well, I'm going to let you explain the story. I do know why they're still in the sky, but I want you to tell that story.
Well, even though if you zoom out a small bit, so we can see it. So they're still in the sky, and normally you're put in the sky as a reward, but in this case, they're put in the sky to be punished. Now that doesn't sound like much of a punishment, but what it means is, the king and the queen are circumpolar, so they go around a North Star, which means they spend half of their day hanging upside down. Now that's not a real nice royal thing to be doing. It's the kings and queens don't want to be hung upside down for half a day. So their punishment was they were put in the night sky by the gods, and so they were circumpolar, so they go around around a North Star. So they spend half of their day upside down, hanging upside down in the sky.
So there is a really cool object that I'd like to point out. And again, after you find this great square of Pegasus here, which we're rotating in, there we go. So I've got the great square of Pegasus. Let me zoom out just a little bit. We can move over to Andromeda here. And I may have to turn off this, turn off my auto-identify feature so that Andromeda fades away. There we go. All right, there's this little disc-shaped thing here. Now, it's nice and bright on your computer screen, and it's easy to spot, and it is obviously a galaxy. In the actual night sky, it's a bit trickier to spot, requires a little bit of training. But again, what you do is you find these 4 stars of the Great Square. That's not so hard to do. And then once you find those 4 stars, you go down 1, 2. And those 2 stars get you to a star called Merak. And again, this is the constellation Andromeda here. And then from Merak, which is roughly where her hips would be, you go 1 and then 2. And that object there, it says M31 on the screen, but that is the Andromeda Galaxy. And what you're looking at, and it is actually, if it's a nice dark sky and you're no moon and you're away from city light pollution, it is actually possible to see the core of it. Now, you don't usually see the extents of the spiral arms or the disk structure, but you usually do see the core kind of starting to fade into a disk. And that is the most distant object. So I showed you the most distant star that you can see in our galaxy. This is the most distant object that you can see without using a telescope at all. The Andromeda Galaxy is something like 4.2 million light years away. Now, I throw this term light year around It's not actually a measure of time, it's a measure of distance. It's the distance that light, traveling at the speed of light, about 186,000 miles a second, can travel after one entire year. The number is very, very close, but not quite 6 trillion miles. So this object is about 4.2 million times 6 trillion miles away, and it's getting closer. It gets closer by about 61 miles every single second. And something like 4.5 billion years from now, it is going to collide with our Milky Way galaxy. Now, I say collide, and you might think, oh my gosh, things are going to be smashing into each other. It turns out it's really more of a merger. And that's because the space between the stars is unimaginably vast in our galaxy and in that galaxy. And so the probability that any two stars will actually hit each other, because there's so much room to miss, is that they will generally just merge in and shuffle and become one really big elliptical galaxy 4.5 billion years from now, and almost no stars will hit any other stars, though there might be just a few collisions. Out of trillions of suns, just a few collisions isn't really much. Okay. The next thing I wanted to point out here is we're coming into the end, is let's take a little bit of a view away from, we'll take a look at the stellar neighborhood here. And so this is our stellar neighborhood. This is our sun, and we're viewing our sun from about 200 light years away. And we can see all these other stars kind of whizzing around in the sky in an unrealistic way that would not be possible if you were actually located 200 light years away from the sun. But what I wanted to show you was a few cool things. So number one, let's turn on the constellations and see what they look like from here. So I'm going to turn on the stick figures, and when I do that, notice all these crazy lines. Now remember, when I showed you the constellations earlier, they form these nice recognizable shapes. These are the same constellations. I promise you the stars in the same spots, and I promise you the lines are connecting all the same things that they were connecting to before, but because we're not on the Earth, those stars in the constellations that all look like they're about the same distance from each other are actually wildly variable. And so some of them are very close, some of them are very far. I'll click on some of these if I can. So this one is Sirius. Sirius is in fact not the closest star, it's one of the closest stars, only 8 light years away from our sun. Proxima Centauri is actually the closest star, only a little over 4 light years away from the sun. And so you can see some of these brighter stars, Fomalhaut, Procyon, and I don't know that one. But in any case, these stars will seem bright in the sky because they are so close. And so the other thing I wanted to point out is, let's turn those off and let's turn on something else that this really just kind of fried my brain when I saw this, which was, I want to see stars that have exoplanets. And so I'll go ahead and turn that on. And what you're looking at now are stars that have exoplanets. So you know that we have these satellites that are looking for stars that have planets in orbit around them. And actually, let's zoom out a bit. I'm taking it out to, there we go, about 670 light years away from Earth is my distance right now. And go out a little bit farther because there's something I would kind of want you to see. Some of these stars have little plus signs, which means that we've actually found lots and lots of exoplanets near them. The way we find these exoplanets is through a NASA satellite called Kepler originally. So there was a satellite called Hipparchus, and it was measuring the distances to all of these things. Hipparchus is no longer functioning. And then Kepler was trying to study these stars to see if it could detect a planet in orbit around them. And you can see it actually found quite a few. Now, this is from the K2 mission. If I go out a little more, where is it? Come on. There we go. There's this cone-shaped thing whizzing around. Let's see if I can put this in location scroller mode.
Just so everyone can understand, looking for a planet passing in front of a star, which is the transit motion it was looking at. is like looking for a mosquito flying in front of a hand torch or a flashlight in California while you're sitting in Michigan. That's how sensitive these telescopes are.
Yeah, so it's crazy difficult, right? So Kepler is looking for this little dimming, and this cone shape structure that you see here. You're thinking, oh my gosh, what luck that there is this particular region in space that has a crazy number of more planets than all the other regions of space, which seem to be pretty much average. No, in the K1 mission, the satellite was pointed toward that part of the sky, and it studied it for a very long amount of time, and it found a whole lot of exoplanets. In the K2 part of the mission, it was looking at many different areas of the sky, but no area was looked at for a very, very long amount of time, which meant that if you had parked it, pointed at that part for a very long amount of time, you would have found a crazy higher number of stars with exoplanets. The other thing I want to point out is the way we find these exoplanets is we're studying and we're looking for things transiting their host star, which means that the solar system we look at has to be edge on. So think about the number of solar systems that are not going to coincidentally be edge on. And also we want to see about a couple of orbits per month. Right now, there is nothing in our solar system that goes around our sun twice in a month, nothing. And that means that if you were a scientist living on one of these other stars and you were using the technology of Kepler to study the universe around you, and you happen to point it at our sun, you would not have found any planets in our solar system at all, right? So when you hear, well, there must not be Earth-like planets out there suitable for hosting life, remember, we don't yet have technology looking for planets that fit that description. So this is just what we're able to find right now. By the way, Kepler is no more. It's been replaced by a new satellite called TESS. So TESS is the new one continuing on the work. Okay, enough of that. A couple of cool things that I want to point out as we come to the top of the hour before I run out of time. Go to my favorites lists. There it is. Okay, so let's take a look at Mars. Okay, so Mars has, so now we're in orbit around Mars. Mars has two moons. One is named Phobos and one is named Deimos. Now in mythology, in Roman mythology, Mars is the name of the Roman god of war. And of course, Romans are thinking that gods would be equipped with the same stuff that they're equipped with when they go to war, except probably a little bit shinier and better. And that was chariots, the most advanced technology they had in Rome to fight in war. And so they imagined that the god of war has a really nice chariot. Nothing more modern than that. And the god of war has two really nice horses, and they happen to be black stallions. And those horses' names are Phobos and Deimos. And in Latin, those names translate to mean fear and dread. Because if the god of war is bearing down on you, you have much to fear and dread. Okay, so let's take a look at those moons. So first we'll take a look at Phobos. Okay, never mind. We'll take a look at Deimos. And so here's an image of Deimos floating out in space. You can see it moving very gently. Not a whole lot going on there. Let's see if I can find my image of Phobos. There's Phobos. And you can see it's also tumbling around. And one thing that might occur to you is they kind of look like lumpy potatoes. They don't look a lot like moons. In fact, you might say they look a little more like asteroids, and that's because they are, in fact, captured asteroids. They're actually very tiny. Phobos is closer to Mars, and Deimos is actually a little farther away from Mars. Phobos actually orbits Mars a couple of times a day. Deimos takes a lot longer. It's in a much higher orbit. And through some interests of orbital mechanics that I don't have time to go into, Phobos is actually spiraling in toward Mars, and one day will crash into the planet. Deimos, on the other hand, is spiraling away. It will never crash into the planet. Next up, we have Jupiter. And if I back up from Jupiter, let's just bring up Jupiter and its moons. Oh, actually, I did the wrong search here. Jupiter, there we go. I open it up and I'll just turn on all of the moons of Jupiter. These are not all of the moons of Jupiter. These are just the major Galilean moons of Jupiter. Their names are Io, Europa, Ganymede, and Callisto. Io is the closest innermost moon. It looks like a some people call it the pizza moon. It is covered with volcanoes. Its surface is completely remade every couple million years. It is the most volcanic object in the entire solar system that we know of. And Europa, Callisto, and Ganymede are ice moons. They're very cold. Europa appears to have frozen oceans on it. Ganymede, meanwhile, is the largest moon in the entire solar system. It's so big that it's actually larger than the planet Mercury. The other planet that I'm going to point out is going to be Titan. It's also larger than the planet Mercury. Titan is actually, however, a moon of Saturn. So if I go to Saturn here, you can see the planet. Let me put this in location scroller mode. You can see the planet. One of the things I want to point out is this interesting gap in the orbit. More on that in a minute. And I'm just going to show you a couple of the notable moons. So Titan, I won't spend time showing you Titan because we're about out of time, but Titan is the only moon in the solar system that has an atmosphere. And not only that, it has liquid on its surface, but it's not water. It's essentially liquid methane, lakes and rivers of it, and it rains. So it's very, very cold there, but it is actually liquid, and it has an atmosphere, the only one that does. The cool things to point out is this moon Mimas here. Mimas looks like the Death Star from Star Wars. If you've seen Star Wars, they have the big space station with the planet zapping gun on the side of it, and that's what Mimas actually looks like. But if I go back to this and its moons, Mimas happens to be at this magical position, distance from Saturn, where when it goes around Saturn just once, an object in this little black gap goes around twice, and that causes whatever is in that position to get a kick. Either if it's just a little bit early, it gets a kick that slows it down and it pulls it into the inner part of the disks. Let me zoom in a little bit for you. It'll go into the inner part of the rings. If it's a little bit later, it'll get pulled up into the outer part of the rings. And so this is being kept clear by this thing caused by Mimas that performs something called orbital resonance. The other thing I wanted to point out, and this is my last fun fact, and then I have to wrap it up, is these two moons called Janus and Epimetheus. Now, this is a freaky thing. What happens with Janus and Epimetheus? I'm going to see if I can flip this more on edge. Okay, Janus and Epimetheus both orbit Saturn at a distance of about 150,000 kilometers. But the difference between their two orbits is just 50 kilometers different. And that means that they are in almost the identical orbit going around at almost the very same speed. And they chase each other around the planet. But they do something very strange, very, very strange. As the whatever moon is on the closer to Saturn, slightly closer to Saturn, will go around ever so slightly faster. It takes about 4 years for this to happen, and it will catch up with the moon that's in the higher orbit. When that happens, when they get close enough, their gravity interacts. And the one that's behind acts like a brake as it tugs gravitationally at the one that's ahead. And that causes it to slow down. Meanwhile, the one that was ahead pulls gravitationally on the one that is behind, and that speeds it up. But when you go into when you gain momentum, you actually go into a higher orbit. And when you lose momentum, you go down into a lower orbit. And that causes them to literally trade places. The one that was in the higher orbit goes to a lower orbit, and it starts going around faster, because if you're closer, even though you're technically moving slower, you have less distance to cover. And when you do all the math, it turns out you get around the planet faster than the one that is technically moving with higher velocity, but in that higher orbit, and it takes longer to get around the planet. And so this is called a horseshoe orbit. They chase each other around the planet over and over, trading places and trading places and trading places. And they've been doing this for who knows how long. That's all I have for you. Thank you very much. And next up, I think we have Mike, and
yeah,
we'll turn it back to Liam.
Sure. So we have, and there are other events starting on other channels. Come back to us at 6:30. We'll have Mike Bruno talking about the size and scale of the solar system. He has some scale models to show. And then Leading straight after that, then we'll go into, or after that, we'll come back again with Tim Campbell, who presented here at 8:30, talking about spectroscopy and how we use light to discover what the universe is made out of. And then again, straight after that, again, we'll have our antenna talk. So we'll come back to Gordon Hansen, and Gordon Hansen will actually be showing you some astrophotography. And actually, since it's cloudy outside, we're actually going to discuss how he takes processing of images that he gets from his camera and turns them into the beautiful images that we see online every single day. So please check out glac.org to find out the schedule of events, but come back to us because we have more in store for you for the rest of the evening.